All right, we're going to take a quick review, look back at solving proportions in multiple dimensions. I'll explain it a little bit more than is in the lesson, but you may need to have a look back at your notes if this lesson is completely foreign to you. You may want to look back at your notes. I believe we did this end of November, beginning of December, something along those lines. But we are going to be facing some questions that are similar to this stuff on our Unit 8 test. So we want to make sure we know what we're doing. Okay, now at that time, what we had been doing is we had been talking about various ratios dealing with similar polygons. Okay, and in those ratios, we were talking about all kinds of different stuff. We were talking about scale factor, we were talking about side lengths, perimeters, areas, volumes, stuff like that. And what we were discovering at this particular point is we were discovering that the ratio that typically is referred to as scale factor, that the information in that ratio can be used towards a lot of different other measurements. Okay, and basically what we said, if we could establish what the scale factor was, and in the case of this slide, it's A to B, where A and B are just some numbers like 1 to 2, 2 to 3, 3 to 5, okay, stuff like that. If we could figure out what the scale factor was, then what we had talked about the day before was we'd said, okay, if the scale factor is A to B, then what that means is that the ratio of the linear measures, which is to say the side lengths, the ratio of the side lengths is also A to B, which made total sense because scale factor came from the linear measures. That's where you got the scale factor from, was comparing side lengths from one figure to another. Okay, so it made sense that the ratio A to B was the same for scale factor and for linear measures. But we also discovered, okay, that same ratio also applies to the perimeters of the figures. And that also makes sense because perimeter is nothing more than a collection of side lengths. Okay, so if the side lengths, if their ratio is A to B, then the perimeters from one figure to another, the ratio will also be A to B. But as you moved into other measurements such as area, okay, this changed things. Scale factor, linear measures, perimeters, those were all first dimensional measurements. Those were measurements that all had length. They didn't have any width, they didn't have any depth. Okay, but as we change the discussion and start talking about area, well, now area is a topic that has length, but it also has width. So it brings a new dimension to the discussion. Okay, so this ratio that we're seeing, A to B, A to B, A to B, okay, that ratio that was going along, the same values went into it, but in order to force them to be a second dimensional ratio, what we did is we forced ourselves to square the values. So that's how come you have this A squared to B squared. It's because we forced the first dimensional ratio to become a second dimensional ratio by squaring the values. The same discussion applied to talk on volume. Volume didn't just have length and width, also had depth. So it brought yet another dimension to the discussion. So once again, the A to B ratio was fine, but we had to cube the values of A and B to get them into the third dimension so that the ratio could apply. But it's the same values all along, A and B. It's just a question of what dimension they're in. Okay. Now, we were applying all of this information on similar polygons. We were using proportions. Proportions are the math of similar polygons. Okay, and we'd been using those proportions to help us find missing side lengths. Okay, and we're still going to be using them to help us find missing measurements. Okay, it's not just side lengths anymore. We can use them to find missing perimeters. We can use them to find missing areas. We can use them to find missing volumes. It just depends on what the problem is actually needing. Okay, but this introduced a new problem. Okay, when we set up our proportion, the thing was we had to make sure that both sides of our proportion were in the same dimension with each other. And if they aren't in the same dimension, then we forced them to exist in the same dimension. And we said that the easiest way to do that, the most straightforward way of doing it, was to cause the smaller of the two dimensions to rise up and become a larger dimension. Okay, so let's take a look at how this was working. Okay, so we start off with something like this. If two similar figures have corresponding side lengths of 2 to 3. The first one's area is 36. What is the area of the second? Okay, well, what we've been doing this unit would be to take this figure, figure out what kind of a shape it is, apply an area formula to it, and calculate the area based upon plugging in missing information into the area formula. Okay, well, this is a relationship discussion, not an actual area calculation, but a relationship from one figure to another similar figure. Okay, and whenever there's similarity, your brain needs to think proportions. Okay, since we're thinking proportions, we're going to look at the problem and see, do we have any ratios that we can plug into a proportion? Whether we have any, yeah, there's one right there. It says that the corresponding side lengths are 2 and 3. Okay, if that's a ratio between side lengths, that's your scale factor right there. There's a 2 to 3 scale factor going on inside of this problem. Now we're also looking for area. Okay, so we got 2 to 3 on side lengths, and we have 36 to unknown as far as area goes. Now, if you put that information into a proportion, it's going to look something like this. We've got 2 to 3, and we've got 36 to a variable. Okay, but the hazard was this. We can set up the proportion. Okay, but we have to double check if we actually got this thing set up correctly. Well, what kind of information is the 2 to 3? It's side lengths. What dimension is side lengths in? It's a first dimensional measurement. On the right hand side, we got 36 to x. What measurements are these? These were areas. Area is a second dimensional measurement. So what our proportion is trying to say right now is that the first dimension is equal to the second dimension. And we need to ask ourselves, anytime we set up a proportion, is that true? Yeah, if we have set up a dimension mismatch, this is a lie. These are not equal to each other. Okay, so once you identify that, no, it's not true, fine. You need to figure out a way to make it true. Okay, so what we said is the easiest thing to do is to figure out the smaller of the two dimensions, which in this case is first dimension, and figure out a way to make it match the larger of the two dimensions, in this case is second dimension. So the easiest thing to do is just take that first dimensional ratio and square the values. Now you've got second dimension on the left because we forced it to happen, and we've got second dimension on the right because that's the way it came. Okay, so just clean it up. You got 2 squared and you got 3 squared. Obviously that's 4 and 9. And then you just cross multiply and solve, just like always. Nothing extra or fancy has to happen to the problem. 4 times x will be 4x. 9 times 36 will be, what is that? Looks like 324 maybe. Yep, got it right. Okay, and of course we don't want 4x's, we just want 1, so we'd divide by 4 just like always, and we'd end up with a value of 81. Okay, now think about what you actually just did there. This is an area. Okay, that's what the problem asked for, was the area of the second figure. We just calculated the area of a figure without having any idea what kind of a shape it is. We don't know if it's a quadrilateral or a triangle or a pentagon or who knows. Okay, but we just found its area without not only not knowing what kind of a shape it is, but also, of course, not having a formula to go with it because we don't know what kind of a shape it is. Okay, once they bring the idea of similar into the problem, okay, that changes the game. Okay, so let's take a look at another one. The following spheres are similar, and the scale factor between them is 1 to 5. What is the volume of the figure on the left? Okay, well, follow along. Let's see if we can get it set up. Okay, once they say similar, that changes the game. We can go, okay, similar. It's no longer about volume formulas or area formulas. It's about a proportion that relates these two figures to each other. Okay, so in order to set up a proportion, we need ratios. Do we have any ratios we can work with? Yeah, we got a 1 to 5 scale factor in between them. That's a good ratio. We're going to use that one. And obviously, we're going to be using volume. It needs to be in the problem because that's what we're working on. Okay, so we got a 1 to 5. and we have an unknown to 125. Okay. All right, we just set up a proportion. Is it true, or did we create a dimension mismatch? Yeah, it's mismatched pretty badly. Okay, we've got scale factor. What dimension scale factor in? It's first dimension. Okay, over here, volume, third. So we just said first dimension equals third dimension. That is so not true. Okay, so we're going to have to fix it. And the way we fix it is by bringing the smaller dimension up to the larger. So what are we going to do to these guys here on the left? We're going to cube them. Okay, we're going to cube them by bringing them to the third dimension. Yes, they're not going to cuba, they're being cubed. Okay. All right, so now we're just going to simplify this cubed information over here on the left, and we'll cross multiply and we'll solve just like always. What's 1 times 1 times 1? Obviously 1. And 5 times 5 is 25 times another 5 is it's 125. Now this one actually turns out to be very easy to solve. You have 1 over 125 equals how much over 125? That one's obviously going to be a 1. It doesn't always work out like that. Okay, but that's the way the numbers are in this case. Okay, so once again, we just calculated the volume of a sphere without even having so much as the radius to work with. Okay, that's a pretty powerful tool to have, but again, that is made possible by the fact that they said the figures are similar. Okay, I've got one more here. Let's take a peek at it real quick, make sure we understand what we're doing. The following shapes are similar. Solve for x. All right, once again, they bring similar into the problem. Our math when we're thinking similar is proportion. So let's look for ratios that we can use. What ratios do you have? 9 over 6, yeah, we could use the 9 over 6, both of them over there in the right side figure. Now remember what I told you once upon a time. The best thing to do is to get into a habit of how you set up your proportions and then follow that habit. And our habit typically is to pick a piece of information from the left and then relate that same piece of information to the figure on the right. Okay, so if you were to go left to right, what would be a good ratio you could use? Yeah, the 15 and the 9. Okay, we'd use the 15 and the 9. Okay, and what would the other ratio be? Yeah, the x and the 6. Okay, so that would be a way to do it. And again, you could absolutely relate the 9 on the right to the 6 on the right. Just make sure the rest of the proportion is adjusted exactly to how you started. Okay. All right. Now, is this proportion okay, or do we have a dimension mismatch here? There is a mismatch, okay? We got x over 6. What dimension is this ratio in? It's a first dimensional measurement. These are side lengths, okay? On the right side, those are areas, okay? So you got first dimension on the left, you got second dimension on the right. Can't do that. Okay, so how are you going to fix it? Squaring which side? Squaring the first dimensional side. We're going to square the left. Oh, yeah, look what happened here. Our variable got squared. Okay, what do you think that's going to change about the problem that the variable got squared this time? Absolutely right, nothing. All it's going to do is it's going to bring an x squared into the problem, which we will have to deal with before the problem is over with. Okay, but that's the correction that needed to be made, so deal with it. Okay, 6 squared is going to be 36. We'll cross multiply. We'll solve just like always. Now, obviously, 9 times x squared is going to be 9x squared. 36 times 15, I believe, is 540. Okay. Now we got 2 issues to deal with. First off, we don't want x squareds, which we'll have to deal with that. And secondly, we don't want 9 of them. Okay, so the best thing to do is, yeah, I don't want x squared, but I certainly don't want 9 of them. So let's clear the 9. Okay, so we'll divide both sides by 9. That'll leave x squared is 60. And then, of course, you don't want the x squared. You want just x. So how do you get that off there? Square root on both sides. Okay, and on this one I did just take it to a decimal. You're going to end up with decimals and fractions and all kinds of things when you're crossing these dimensions. A lot of times you do not end up with whole numbers. Okay, but that's the way this is going to work. Okay, so hopefully that is enough of a review to get your brains back going in that direction. I do have a worksheet that I put together, and you may recognize it. It's very much the same as the worksheet that we did 2.5 months ago. Now, being as this is a review topic, I'm not taking this worksheet as a grade. I'm telling you, I think you would be a fool to not have a look at it, not figure out how this stuff works, because like I said, it's been 2.5 months since you worked on this stuff, and you're going to see some questions here in about 2 days that are going to deal with this stuff. So don't just disregard this worksheet thinking, oh, it's not a grade, well, I just won't do it. Yeah, you'll pay for that and then some when Thursday rolls around. So you may want to go ahead and have a look at this, and that will wrap up our information on Unit 8. You will have a review tomorrow and a test on Thursday.